So I've been talking about this already, but we're going to talk a little bit about sound again. There's this idea that sound actually travels at different speeds depending on the temperature. Oh my gosh. So what I was saying earlier was that when sound travels, we actually have different regions. And remember, we called the bunched together air particles the compression regions. And we called the spaced out regions of a sound wave the rarefaction regions. And so sound is a wave. But what we found is that if you play a sound and you have a distance over which that sound travels, you can calculate how fast the sound is traveling. So if we had a speed axis in meters per second and we graphed it as a function of time in degrees Celsius, it turns out that as the air gets warmer and warmer, the sound actually travels faster and faster. Because really, this is going to generate for us a y equals mx plus b equation. And when people have experimentally done this, we say that the speed is equal to, the m value. In this case, the x is occupied by the temperature in degrees Celsius. Now I'm going to write T subscript degrees Celsius so that we don't get confused with period, because this is temperature, plus the b value, which is the y-intercept. And so this is actually graph data. Hello? Yep. Yep. So, yes, yep. He's on his way. So 0.59 times the temperature in degrees Celsius plus 332 meters per second ends up being the m value and the b value for that equation as experimentally determined. Okay. Now I'm going to give you a little quick tip on this one. Check your equation sheet. Because our textbook gives one version of this equation, because since these coefficients are determined experimentally, it's going to depend on whether you do it at sea level or what the elevation is when you do this experiment. So our textbook uses one equation with different coefficients, and our workbook uses another version of the equation. It's not a universal equation. It really does depend on the atmospheric pressure, okay? So I'm going to say check your equation sheet, just because there's a different equation for textbook versus workbook problems. And that has everything to do with the fact that this is an experimentally determined equation for the speed of sound based on the temperature of the air in which it's being transmitted. Okay? And so with this idea, how long will it take for sound to reach an ear if there's a tuning fork that produces sound? Here's the ear that we're talking about. We'll add in an ear. Oh, that doesn't look like much of an ear. Anyway, that's an ear. And if we have an ear that's a distance of 20 meters away from a tuning fork. Now, if you don't know what a tuning fork is, it's literally like a piece of metal like this. It always has the frequency stamped on it. So this one goes at 512 hertz. The one that we're talking about on the page goes at 1,000 hertz, but that's 512 hertz, okay? Here's another one. Notice it has shorter arms. You guys hear that's a higher frequency? And this one has stamped onto it 2,048 hertz. And they typically are C notes. They're actually used historically for tuning things. Now we would probably use an app for it. My daughter uses an app for tuning her guitar, but we used to tune things based on these tuning forks. That's why they're called tuning forks. So how long will it take for the sound to reach? Well, speed is equal to distance over time. That's true. So delta T is going to be equal to delta D over V. And in this case, the delta D is 20 meters. And the speed, according to this information, is 340 meters per second. So I do some quick calculations, and I end up getting 0.58823 seconds. Not long at all. So it's not like, oh, I missed a zero. 0.058823. Not long at all. And we could round this off to sig figs. Looks like it's like maybe 3 significant figures. So 0.0588 seconds. This is fast. That's why you hear things so quickly. What's the temperature though? Well, if V is equal to 0.59, and actually the units on this coefficient are meters per second per degree Celsius. So the units are actually kind of ugly on that one. Times the temperature in degrees Celsius plus 332 meters per second. Again, I can do some algebra on this, and you can check this for yourself. Make sure you can do this. I'm just going to rearrange it all in one go. I would get temperature all by itself in degrees Celsius as being V minus 332 meters per second, all divided by that 0.59 meter per second per degree Celsius. 0.0588? Yeah, that's what I wrote. Yeah, I think I said 0.5 and I wrote 0.05. Yep, you got it. But that means that I could use the speed of sound almost like a thermometer. And if I plug all these values in, I get 340 meters per second minus 332 meters per second over 0.59 meter per second per degree Celsius. And I get the temperature of that air to be 13.559 degrees Celsius, or about 13.4. Now I feel like I didn't give myself enough space for that one. The follow-up for this is, what's the wavelength? Well, for this, I think I would want to use V equals lambda f, right? I can get at it, because I know the frequency of the tuning fork. I can get lambda all by itself, V over f, 340 meters per second, divided by 1,000 hertz frequency. And like I said, tuning forks typically are C notes. There really is not a 1,000 hertz tuning fork typically. A C note would really be 1,024 hertz. I just rounded it off to make the numbers easy. But 340 divided by 1,000 is going to be 0.34 meters. I got one quick little thing here. I got a flamingo sitting on a dock, and this flamingo has water washing up towards it. 2 meter per second wave. Flamingo sees the wavelength is lambda, 4 meters. Find the time between toe wettings. What we're really looking for here is find the period, because that's how long it's going to take between the flamingo getting her toes wet. So I say V is equal to lambda f. So F is equal to V over lambda. Now I could have also said V is equal to lambda over period, which would mean that period is equal to lambda over V. See how those guys are really just reciprocals of one another? And so based on the givens that I have, I think that I would use that second variant, and I would say that the period is equal to, well, the lambda is 4.00 meters. The speed is 2.00 meters per second. And that means 4 divided by 2, our flamingo is going to get their toes wet every 2 seconds. That's the period between crests of water hitting the flamingo's toes. Therefore, the bird gets their toes wet every 2 seconds.